Alright, this is Honors Geo, Chapter 5, Section 3. Angle and triangle, well, angle bisectors. Alright, so this one deals with two theorems, the angle bisector theorem and the converse of the angle bisector theorem. And what the angle bisector theorem says is that if I have an angle let's call it BAC, and I have some ray that goes through angle BAC such that it cuts it in half as best as it can, of course. As best as it can. And we call that ray AD. If that happens, and it cuts this angle in half, so these two guys are the same. If I was to draw a point, or a line rather, from this guy to this guy, the shortest distance, from this guy to this guy, then two things. Thing number one, they would be perpendicular. And thing number two, they would be congruent. So what the angle bisector theorem says, here it is. If a point is on the bisector of an angle, then it's equidistant from the two sides of that angle. If a point is on the bisector of an angle, so point D, then the distance from D to B and from D to C are going to be the same. Moreover, they will also be perpendicular. So, angle bisector theorem, if AD bisects BAC and BD is perpendicular to ray AB, and DC is perpendicular to ray AC, then I have enough information to say, based off the angle bisector theorem, that BD is notice when we're dealing with the angle bisector theorem, it doesn't say that BD is congruent to DC. BD is equal to DC. So we're dealing with equality, not congruency with the angle bisector theorem. Converse of the angle bisector theorem says the opposite. So we're switching it. So the converse of the angle bisector theorem says that if a point on the interior of an angle is equidistant from the sides of the angle, then it lies on the angle bisector. So the converse says if BD is perpendicular to AB and DC is perpendicular to AC, and BD is equal to DC, then I have enough information to say that AD bisects angle BAC. Right, so angle bisector theorem and the converse of the angle bisector theorem. Okay, with that you can do various algebraic stuff. For example, here we have, this is 27, this is 27. That tells me that they're both congruent angles. That means that this guy is being bisected, and this is perpendicular, and that's perpendicular, so I know that these two guys are the same. So I can say that x is the same here based off of the angle bisector theorem, and this is 15. Here, I'm told that this is the same and this is the same, so these two, and it's perpendicular, so that means that these two angles must be the same. So I can just solve for x by setting these two equal to each other. So subtract 3x from both sides. You get 5 equals x minus 6. Add 6 to both sides. X equals 11. Super duper straightforward. Here, same thing. I know that these are bisected. These are perpendicular, so these guys based off of angle bisector theorem must be the same. Therefore, I set these two guys equal to each other. Subtract 6x from both sides. I get negative x equals negative 5. X equals 5. Do I have enough information to conclude that? I do not. And the reason why I don't conclude that this is the angle bisector is because I don't know if these are perpendicular. It looks like it needs to be a little shorter. These are perpendicular intersections between the segment and the end of the ray. So I need it to be perpendicular, and I need these two guys to be the same. So I do not have enough information. Concurrency of bisecting angle bisectors of a triangle. So we talked about concurrency, but to refresh your memory, concurrency is a point where 3 or more lines intersect, and the point that they intersect on is called the point of concurrency. So for theorem 5.7, we have this triangle ABC, and they all are being angle bisected. So the angle bisector comes this way. The angle bisector comes down this way. The angle of course not this guy, comes this way. And they meet at this point. Where they all intersect at this point of concurrency. What the concurrency of angle bisectors of a triangle says, and they meet at point. That meet at point P. What it says is at that point of concurrency, if I go straight down, straight down, right? Based off of the angle bisector theorem, this is basically acting like the angle bisector theorem 3 times around. Here's the guy, so this guy and this guy must be equidistant. Here's the bisector, so this guy and this guy must be equidistant. Here's the bisector, so from that point, so this guy and this guy must be equidistant. So these guys are all the same, just like the angle bisector theorem, and they form 90-degree angles, which is helpful because we can use this to solve for all various sides. So with the concurrency of the angle bisector of a triangle says that the point angle bisectors of a triangle intersect at a point that is equidistant from the sides of the triangle. So, if AP, BP, and CP are angle bisectors, then no, I should have D, E, F. Then P, D is equal to P, E, which is equal to PF. Right. When we draw a circle within a triangle at the point of concurrency, we would call that guy the end center of the triangle when we're dealing with angle bisectors. The point of concurrency of three angle bisectors of a triangle is called the end center. Before we talked about the circumcenter when we did the previous section. So now this is the end center. Alright, so with that we can do stuff. Since we know that this is perpendicular, we have right triangles galore, so we can use the Pythagorean theorem to solve for various things. So here it says example 4, suppose you are not given AF or AN. Yeah. Okay. But you're given BF and BN. So here's my BF, here's my BN. So if I was to write this out, it kind of looks like this. So we have BF, and then we have BN. Right, I know it's a right triangle. And it says that BF is 12, BN is 13. This is the Pythagorean theorem. So it's A squared plus B squared equals C squared. So that's 13 squared equals 12 squared plus B squared. Let's just call it NB squared. Okay. 144 plus NB squared equals 1, I believe it's 69. Subtract 144 from both sides. NB squared equals 169 minus 144. Let me double check. And I get NB equals 25 square root NB is equal to 5. Okay, so with the end center we can use the Pythagorean theorem quite a bit and solve for various sides. And that is that section. Hope you have a great rest of your day.